In this lesson we will discuss Kirchhoff's voltage and current laws. Kirchhoff's voltage law, abbreviated as KVL, may be stated as follows. The algebraic sum of the EMFs and voltage drops around any closed circuit is zero. A convention for the signs of the voltage drops or rises must be adopted. Generally, if the negative polarity is first encountered, the sign of the voltage is positive, a rise, and if the positive polarity is encountered first, the sign of the voltage is negative, a drop. Examine the circuit shown. Moving clockwise in the direction of the arrow in the loop ABCD, we find the voltages V1 and V2 are negative and E1 is positive. Thus, minus V1 minus V2 plus E1 is equal to 0. Moving clockwise in the second loop AEDCB, we have E2 minus V3 plus V1 is equal to 0. Since V1 equals I3 times 200, V2 equals I1 times 500, and V3 equals I2 times 300. We can rewrite the first two equations as minus 200 times I3 minus 500 times I1 plus 15 equals 0, and we will call that equation 1. And 10 minus 300 times I2 plus 200 times I3 is equal to 0, and we'll call that equation 2. Now, using the outermost loop, AEDFA, we have E2 minus V3 minus V2 plus E1 equals 0, or 10 minus 300 times I2 minus 500 times I1 plus 15 equals 0, or minus 500 times I1 minus 300 times I2 equals minus 25, and we'll call that equation 3. We observe there are three unknowns, and hence another equation would be useful. We can now use Kirchhoff's current law, abbreviated as KCL, which states the algebraic sum of the currents at any junction of conductors is 0. At junction D, we can use Kirchhoff's current law, using the convention that currents that are leaving the junction are negative and currents entering the junction are positive. We have I1 minus I2 minus I3 equals 0. Therefore, I1 equals I2 plus I3. Now, substituting I1 equals I2 plus I3 in equation 1, we have minus 200 times I3 minus 500 times the quantity I2 plus I3 plus 15 equals 0. Or minus 200 times I3 minus 500 times I2 minus 500 times I3 equals minus 15. Reducing further, minus 500 times I2 minus 700 times I3 equals minus 15, or 500 times I2 plus 700 times I3 equals 15. We'll call that equation 4. And 300 times I2 minus 200 times I3 equals 10. We will call that equation 5. Multiplying equation 4 by 3 and equation 5 by 5 yields 1500 times I2 plus 2100 times I3 equals 45, and we will call that equation 6. 1500 times I2 minus 1000 times I3 equals 50, or equation 7. Subtracting these equations results in 3100 times I3 equals minus 5. Therefore, I3 equals minus 5 divided by 3100, or minus 1.6 times 10 to the minus 3 amps, or minus 1.6 milliamp. The negative sign indicates that the current is leaving the junction. Substituting for I3 in equation 5, we have 300 times I2 minus 200 times minus 1.6 times 10 to the minus third equals 10, or 300 times I2 equals 10 minus 0.32. Solving for I2 gives I2 equal 9.68 divided by 300 equals 32.2 milliamps. Now solve for I1, where I1 is equal to I2 plus I3, or 32.2 plus the quantity minus 1.6 equals 30.6 milliamps. Solving for V1, V2, and V3 results in V1 equals I3 times 200, or minus 1.6 times 200 times 10 to the minus 3, or minus 0.32 volts, or approximately minus 0.3 volts. V2 equals I1 times 500, or 30.6 times 10 to the minus 3 times 500, or 15.3 volts. V3 equals I2 times 300, or 32.2 times 10 to the minus 3 times 300, or 9.67 volts, which is approximately 9.7 volts. Checking, we find that minus V1 minus V2 plus E1 equals 0, or minus the quantity minus 0.3 minus 15.3 plus 15 equals 0, and E2 minus V3 plus V1 equals 0, or 10 minus 9.7 plus the quantity minus 0.3 equals 0.